Welcome and thank you all for standing by. Participants will be in a listen-only mode until the question and answer session. At that time, if you would like to ask a question, please press star then 1. Today's call is being recorded. If there are any objections, you may disconnect at this time. I would now like to turn the call over to Mr. Phil McLeod. Sir, you may begin.
Thank you very much. I'd like to welcome everyone to our webinar this afternoon. This is one of a series of webinars that we've developed for the Mississippi River Basin initiative, and MRBI identified 9 areas where we need training, and drainage water management is on that list, so we're going to hit that mark today. We have 4 speakers today. First, we're going to have Pat Willey, who is a wetland and drainage engineer from the West National Technology Support Center. Next, we'll have Dr. Hamid Farahani, who's the water management engineer here in the East National Technology Center. Then Dr. Ruth, who's the state conservation engineer in Illinois. And then Jerry Walker, who is the agricultural engineer in the Central National Technology Support Center. If you would like to receive CCA credits for participation in this webinar, we have a CCA form that you can download from the handout section, which is up at the upper right-hand corner of your screen, as shown in the slide that's up there right now. So you can download that screen. There's also handouts from today's presentation that are available. Here's just a quick look at the CCA form. If you're interested in getting those CCA credits, you need to fill out the information there and then either fax or scan and email the CCA form to Holly Kirkendall here at the East National Technology Support Center, and she will take it from there and send it to the USDA office. We're going to have question and answers at the end of the session. There's 2 ways to ask questions. You can either ask a question verbally through the operator by pressing star 1, or you can use the question and answer function that's on the software for live meeting, where it says Q&A on the top of your screen, and you can type in your question, and you'll be read those on our screen, and we'll answer those questions as we get to them. You can type those questions in as they come to you during the presentation as well, and we'll address them at the end. So with that, I think we're ready to go, and I'm going to turn the mic over to Pat Willey and let him begin his presentation. So Pat, take it away.
Okay, thank you, Phil. And today it's Drainage Water Management Awareness, Basic Principles and Practices. And second, let me adjust my screen. Okay, the training outline today, it's background and orientation by me, and then drainage systems by Hamid. Ruth will go over drainage water management for subsurface systems, and Jerry Walker will go over DWM for surface systems, and then Hamid will do the wrap-up. On my talk, I'm going to be going over MRBI team and ag water management team, the basics of DWM, the downstream environmental impacts of nitrogen and phosphorus, and then the DWM requirement for the N strategy, nutrient strategy that we have that came out last fall. The Mississippi River Basin team, initiative team, that's the one that Phil went over. It covers the Mississippi River Basin, most of the states that service watersheds to the Mississippi River. Their goal is to improve water quality and wildlife habitat, and they're doing that through the different programs, the Conservation Partnership, Cooperative Conservation Partnership Initiative, the Wetlands Reserve Enhancement Program, WREP, and CIG, and other programs. We have an ag water management team. Most of you may be aware of that by now. It was formed last March. and it's headed by Paul Sweeney. Paul is the former state conservationist in North Dakota, and he's on this special assignment. It's a 2-year assignment, and the team includes NHQ disciplines from Washington, D.C., and then the NHQ program specialists, and then we have the National Technical Support Center representatives, and then representatives from the states. We have team advisors that are from ARS, Ag Research Service, Purdue University, and North Carolina State University. That team does regular teleconferences. We're meeting every 2 weeks right now in teleconference, and we're developing a program for the advancing drainage water management. The scope of that team is national. It's not just for the Mississippi River Basin. And right now our focus is the upper Mississippi River Basin. Our goal is to reduce nitrate loading to the streams and reduce the ag impact on the Gulf of Mexico hypoxia conditions. And the way we're doing that, the way we're addressing that is to implement drainage water management to reduce nitrates leaving the drained farmlands. So what is drainage water management? It's a Practice Standard Code 554, and it's the employment of a structure for water control, Code 587, in the drainage water line. The structure for water control is a separate practice, but that's the structure in the system, and it's to provide the capability to manage the flow from an agricultural drainage system. It typically involves raising the outlet elevation of the drain, and it results in reduced flow from the outlet. Then the question is, do outlet structures eliminate the flow from the drain outlet? Well, maybe. When the outlet is initially raised, the outflows may stop. You can get a little leakage through some structures, but basically the flow out the outlet is going to stop. And then as flow continues to enter the drain upstream from the structure, the water table will begin to rise within the field. And once the water table rises to the elevation of the raised outlet, any additional rise in the water table will result in a discharge to the outlet. So it's not a plugging of a drain, it's a management of that drain water. And how can DWM help? It's been shown to reduce the stream loading of nitrates by agricultural drainage systems. And the amount of inloading that is reduced is in the range of 40 to 50% in test trials. And the reductions are in proportion to the reduction in drainage water that comes out the outflow. We're only talking about removing or reducing the flow during the off-season or the wintertime, early spring, late fall seasons. So during that period of time, we've been able to hold back about half the water that flows out during a particular year. And I'd like to note that the concentration of the nitrates in the drainage water does not seem to change much during the year. So about half the water held back gives you that approximately 50% reduction in nitrates. Why are we focusing on DWM? NRCS recognizes nutrient loading to streams as a national concern. The drainage water is a significant source of nutrient loads, and the impacts of the Gulf of Mexico and other receiving waters are significant. Does the DWM affect crop growth? Now, that's a question that's often asked by producers. So they want to know, does it help crop growth or hurt crop growth to install the practice? And during the non-growing season, DWM does not adversely affect crop production. During the growing season, some benefits may be observed by managing the elevated water table in the field. So it's not conclusive, not statistically conclusive anyway, but we do see some minor increases in production. Now and then you get statistical observance that shows it might decrease a little bit, but is variable. So we don't have anything conclusive right now on that. So we're looking at basically a minimal effect to production during the season. If you do have some special cases where you can manage your subsurface water and provide the extra water to the root system, during a drought year, you probably will see some improvement in production. The expectations for DWM, it's all about management and not about draining new acres. We're getting a lot of questions from people about how can we do more drainage, and it's not about more drainage. It's about managing the water that's flowing out right now. So we're actually reducing the flow out the end of the drain pipe. The focus is to manage the draining water for improved environmental outcomes and sustaining crop production. And we want to use a conservation systems approach. We're not just applying drainage water management without also applying nutrient management, conservation tillage, crop rotations, or other practices such as cover crops. And consideration must be given to neighboring or downstream hydrologic effects. We are looking at lateral seepage that goes off-site, may affect a neighbor. We're looking at stream flows. We're looking at any kind of changes in the hydraulic conditions, flooding, and groundwater conditions. The environmental impacts of excessive nutrients can be large. Hypoxia is one, and drinking water quality is another. We have hypoxic conditions in the Gulf of Mexico and the Chesapeake Bay, and the hypoxia is the condition in which dissolved oxygen is below the level necessary to sustain most aquatic life. And what causes hypoxia? The biggest cause is nutrient loading. And nutrient loading to the Gulf of Mexico is the nitrogen and phosphorus. Nitrogen's probably got the biggest impact over phosphorus, but it depends on the particular aquatic growth that you have as to whether it is phosphorus or nitrogen. The Mississippi River provides 90% of the fresh inflow to the Gulf of Mexico, so it is significant. And the nutrient-enhanced primary production is it's the enhanced growth of aquatic plants and protists. So that's the algae and the diatoms in the Gulf of Mexico. And these plants and protists die and sink to the ocean floor, and then they decompose, and that decomposition consumes oxygen in the water. And we have a lack of mixing in that strata in the water column, and that lack of mixing causes low oxygen levels near the ocean bottom. The scientists have defined hypoxic conditions in the northern Gulf of Mexico as a concentration of oxygen that is less than 2 milligrams per liter. Now, in other oceans of the world, that limit may be different. It could be 3 to 5 milligrams per liter, but it's low oxygen. It's not near saturation. So in the Gulf of Mexico, it's identified due to species type, and it is a kind of a temperature-dependent thing, too, because as your temperature changes, the need for oxygen by the organisms changes. Hypoxia develops near the ocean floor, and it affects both shrimp, oysters, and bottom fish, all the bottom dwellers. The oxygen concentrations are stratified. When you look at the water column, near the surface you get a lot of wind action, and you can have oxygen concentrations greater than 8 milligrams per liter. Down at the bottom, it's going to be 1 or 2 milligrams per liter. And that hypoxic zone is broken up by wind action in the late summer when the water column is destratified and oxygen concentrations return to normal. Our human health concerns are that excessive levels of nitrate in drinking water can cause human health problems. The short-term health effects occur because during digestion, nitrates transform into nitrites, which diminish the transfers of oxygen in the blood. That can result in a condition called methemoglobinemia or blue baby syndrome. It's a condition that results from high nitrates in the blood. This can be an acute condition in which health deteriorates rapidly over a period of days. The symptoms are shortness of breath and blueness of skin, and the results can be fatal. It especially affects infants. So we need to be really concerned about nitrates in our drinking water. The environmental and ecological concerns of hypoxia are that you have high aquatic species mortality, habitat loss, food chain alterations, and loss of biodiversity. Anytime you get a change in your food chain alteration, you lose some species out of the food chain, you're going to lose biodiversity. And then there are reproductive problems for fish when they're in an environment of low oxygen content. They don't reproduce so well. So that, and then the fish get a little bit slower. There can be increased susceptibility to predation. The sources of the nutrients in the Gulf of Mexico are basically agriculture. If you look at this table right here, you can see that commercial fertilizer, that's all forms of nitrogen, provide in the Mississippi Basin above the Missouri River about 55%, 54.3 in this table. Livestock manure adds about 26%. Legumes add about 10%, 10 to 11%. So you're looking at whether you're in the Mississippi above the Missouri River or if you're looking at the whole Mississippi Basin, you're looking at 85 to 90% of the nitrates are coming from agriculture. And here are two maps. The upper one shows the nitrogen inputs in 1991, and you can see the red area is this is the highest concentration of nutrients going into it. It's of the nitrogen inputs into the system. And if you look down at the bottom map, you can see that the average stream yields are highest in those zones too, and these stream yields, that's the concentration of nitrates or the pounds per acre per year added to the system, to the streams. And here you can see the fraction of the counties drained in the Mississippi River Basin. That's tile drainage. You can see that the areas correlate well to the region that is heavily where nutrients are heavily applied. So we're really interested in that area right there for our actions. Then we have we talked briefly about our nutrient management strategy before this conference. This is a big push by NRCS to apply drainage water management on the land where tile and subsurface drainage systems exist. And to qualify for financial assistance on Nutrient Management 590, we are requiring that drainage water management be required if the land is drained and if drainage water management is feasible. Now, we base feasibility on things like slope, soil type, existence of pattern drainage, and how many acres you can affect with a single structure, so it's an economical consideration too. And those issues are addressed by each individual state. IWM is also required under this strategy if the land is irrigated, and then if it's both irrigated and drained, both of the above practices, IWM and DWM, are required. I'm now going to turn it over to Hamid for the second presentation.
Thank you, Pat. Good afternoon. This is Hamid Farahani, and I'm the new water management engineer stationed at East National Technology Support Center in Greensboro, North Carolina. I would like to start by acknowledging the MRBI coordinator, Ms. Dina Willey. She is with NRCS in Kentucky. I am, as Pat alluded to, there is really no silver bullet to reducing nutrient loading. Drainage water management, as we discussed today, is one avenue, hopefully implemented in a systems approach alongside other conservation practices. That's basically the take-home message that we will emphasize again later. I am the primer today, so my presentation is really kind of a warm-up discussing some of the basics of drainage leading up to the next two presentations that look more in-depth as how drainage water management is implemented. I'd like to start with what we call subsurface drainage systems. I have two facts here. Drainage has been around in America since 1700s. In fact, the first drainage law was enacted in New Jersey, if I read the history correct, back in 1772. Also, I thought this was interesting. Controlled drainage, which is another way of saying drainage water management in a different form, was initiated in 1930s. Some of the work I saw, at least I have seen in the 40s or some literature, goes back to Florida. I'm not quite sure where all the work was done, but this is nothing new we are discussing today. I think that is the message here. We are just hoping to create a greater awareness, and hopefully the goal of NRCS and other practitioners is to enhance the adoption of this technology. I'd like to start here by talking about what is called subsurface drainage by open ditch. I have a drawing here. This is basically anytime you have a water table, shallow water table, any opening into that water table, the water is under positive pressure. Any opening, whether it's a ditch or whether it's an opening for a pipe, water will start flowing. So some of the early drainage systems were basically open ditch. These are cheaper relatively, and all you need is basically a ditch through the soil profile. This is not as common. It's probably more common in lower Mississippi coastal areas, in eastern North Carolina. We see some of that. And in many parts of the world, particularly in less developed countries where they don't have the means to install pipes. So one of the reasons I have here, there has been some confusion as, sometimes we refer to as subsurface drainage by open ditch, we refer to as surface drainage. And the discussion today, the webinar today, has nothing to do with surface drainage because that's confusing, and it also could be interpreted as draining the soil surface. What drainage water management or practice standard 554 refers to is it is only concerned with manipulating the water table, so it's a water table management, and not control or manipulation of excess surface water. And I'll come back to that, and it would be made more clear later by Jerry Walker. So here's a picture I have of a drainage ditch in action. Now these open ditches are usually relatively deep, so they can reach the water table. Now, we could also have subsurface drainage by a drain pipe, and this is more prevalent in the Midwest, in the West for salinity control, and again in many parts of the world. And here's a better drawing that I borrowed from University of Minnesota extension publications. Now, to make the matter surface drainage and drainage ditch and subsurface drainage a bit more clear, I borrowed this good drawing from Dr. Applebaum at North Carolina State University. Let's look at the picture on top. As you see, there is a shallow drainage called surface drainage. It's basically directing the water to a drainage ditch. Now, the drainage ditch in this case has two functions. One, to collect the surface water, and the other is to also lower the water table. And he has a very nice drawing on the bottom. You can see again the emphasis here is that whether it's a deep ditch or whether it's a subsurface pipe, the idea in drainage water management, as far as we are concerned at this stage, is to manipulate the water table. Subsurface drainage by a drain pipe. Again, in this case, we could look at what has been done in the past. Pretty much the practice started with mole drain. I'm sure many of you are familiar with. It's basically a mole chained to a subsoiler and pulled behind the tractor. That practice is really not supported anymore, perhaps not practiced in many places, but it has some applications. It's relatively cheap. So if you have a field that needs drainage to be installed, perhaps a mole drain can at least drain the soil so one can get into the field for subsequent operations. The next generation of advances in drainage came with the creation, manufacture of clay and concrete tile drains. These are not perforated, so they're placed next to each other with an inch or less spacing in between to allow water to enter. And but most modern drainage systems use perforated corrugated plastic drain tubing. Usually these are 4 to 6 inches in diameter. Benefits of drainage, some of this was mentioned before. Pat also mentioned we are looking at about 25% of the land in this country is under drainage. I have listed some of the benefits. Perhaps the number one historically has been enhanced trafficability, so you can get into the field. Also, it's desirable to have warmer, drier soils as spring planting. That's what drainage provides. Protection from excess soil water and improve yield. But the drawbacks, I think the drawbacks is really the main drawback is this unrestricted flow. The unrestricted flow causes nutrient loading of streams, and as Pat mentioned, the hypoxia in the Gulf of Mexico is mostly attributed to lands way north in the upper Midwest. So this is quite concerning. From disposal to management, I kind of follow here one of my drainage mentors, Dr. Gary Sands, and I thought he had a good point. Historically, traditionally, we have been disposing of drainage water, but the shift is now, and for the foreseeable future, until we have a better technology, is moving toward the management of the drainage water. And so you can see the problem: unrestricted drainage provides no control on discharge volume and or timing. And you know, as the rain comes, the system drains, and that could be the day after the fertilizer was applied. So that's now the solution, as has been mentioned. You know, controlled drainage, bringing some control into the management would require some kind of control. So this practice 554 really discusses placing strategic controls in parts of the field, and some of that would be discussed later by my colleagues. Now, the basic premise in drainage water management is really, I should say, the basic practice is to hold water back, except at planting and harvest. That's as simple as that, and it can be certainly much refined under field conditions. I had an animation here by Bell Museum of Natural History. It's really nice to see. Unfortunately, I was not able to upload the video. It would have created complications, but I left a slide here. If you want to see it, you can go there, or if you let me know, I can send you the video. Here's another view of, you know, when we're looking at drainage water management, we're basically trying to manipulate the water table. Let's say we are starting at the left-hand side of this graph with water table during the fallow season at some very shallow depths below the soil surface. As we approach, the idea is as we approach planting, we can lower the water table, allow the soil to dry, complete our planting and cultivation practices, and then raising the water table back up, holding the water back in the soil profile at some depths, shallow depths below the soil surface. But gradually, as the roots grow, we will lower this water table again until the time of harvest, and then the cycle would repeat itself. Is drainage water management effective? Pat discussed this. I'd like to also show you a graph that I borrowed from Dr. Gary Sands that shows, what he has seen, at least 40% reduction in outflow. Now, what the graph shows, the vertical axis is drainage volume without drainage water management, and the x-axis is drainage volume with drainage water management. And the slope is about 1.42, so that's where the 40% comes in, and also 40 to 60% reduction in nitrogen. But the next two questions have been interesting. They've been particularly, I've had a good deal of interest in where does the water go? If you're reducing discharge, people have been asking, because we are not stopping the rainfall. The rain keeps coming. We have to have a budget at the end of the year. That means we are saving 40% water. We are reducing the outflow, and what is that 40%? Research shows that under drainage water management, we have increased ET, or evaporation, and that's mostly because we are holding the water table closer to the surface, enhancing soil evaporation, and also promoting greater crop transpiration. Increased leaching, that has been a concern. I have asked some of our experts, particularly in the upper Midwest, some of the faculty at the universities. They argue that the increased leaching is not a factor because, after all, these soils have such a low permeability, and because they have drainage problems, so you wouldn't expect leaching to be enhanced under drainage water management. We're definitely creating the potential for increased runoff. We have to be aware of that and know what conditions could magnify that problem. And certainly part of the water that is not drained is because we have increased the soil storage. So that's and the next question is where does the nitrogen go? The nitrogen has been there has been almost a one-to-one relationship between the reduction in outflow and decreased nitrogen loading. There's an increased denitrification because of the anaerobic conditions created for a longer periods of time during the year. And certainly there is increased time for crop uptake of nutrients that can also contribute to some of the reductions. Drainage water management is only a part solution. This is an important concept to convey. I'm sure you're all aware of this, but employ drainage water management with other practices in a systems approach to environmental and economic sustainability to be most effective. Some of those practices, we won't have the time to go through these practices. I have some of them listed here. For example, complementing conservation and drainage practices could be nutrient BMPs, bioreactors, two-stage, managed ditches. We have miles and miles of ditches, and certainly they provide the opportunity to hold back the nitrogen. So the concept is as long as we can hold back the water and we can hold back the nitrogen, we create the environment for either the nitrate to be denitrified or to be consumed by plants and vegetation. Buffers, improved drainage design or precision drainage obviously would be helpful. winter cover crops and water storage or nutrient retention basins. And I'm going to stop here and just pass. I'd like to have my colleague, Dr. Ruth Book, to continue ahead. Ruth, would you please take it away?
Sure will. So I'm going to focus on what happens on your subsurface drainage systems when you try to accomplish drainage water management. And this is probably the type of system that NRCS has the most experience with. And today I'll give you a little bit of an overview about what these things look like when you put them on a subsurface drainage system. How do they work? And where do they apply? What are the limitations to putting these systems in on subsurface drainage systems? I'll talk a little bit about how that nutrient loading reduction happens and how we might be able to measure what's going on, any benefits that we might be able to achieve, and summarize the requirements of Practice Standard 554. Here's a graphic for you to show just the general concept of what's happening when you do drainage water management on subsurface drain. Picture for yourself your typical tile outlet right there by a drainage ditch. And here's a schematic of that, tile draining towards a drainage ditch. And the idea is to drain that field only when you need to drain the field. So those times would be when you need to grow crops, for example, or do field work or stuff like that. How are we going to make that happen? Well, we're going to need to put some kind of structural measure in, because otherwise water does what water always does. It flows downhill, and by golly, it's going to go right out the drain tile. So the idea is to put a water level control structure in, as I've sketched in here. And these structures typically get installed on the end of the drainage tile some distance away from the ditch and involve some riser boards or flash boards that get put in so that the elevation of that water table gets raised to however high you put in those flash boards. So you can see in this picture, drainage water moving down that tile is going to run up against your riser boards that you've put in there. In order to escape the tile, it has to go up. And it's going to fill up that pipe and get higher and higher in the field until finally it can escape over the top and go on out to the drainage ditch. So that's how these things happen. I wanted to note for you again, although we've mentioned it before in this presentation, that the work we're doing on these tile drainage systems is really just a way to control the outlet of the drainage system and reduce the flow of drainage in selected parts of the crop year. So we're not intending to go out and increase any amount of drainage out in the field. We're not proposing to add any kind of surface inlets or underground outlets into the system. We're just proposing to take a look at what's happening right there at the outlet of the tile before that water gets a chance to go into the surface water. Here's a schematic, sort of like the one that Hamid just presented, to give you an idea how you might go about managing things in the field once you have that infrastructure installed. And this is a hypothetical year. You can see some dates there across the top, and then the vertical axis is a schematic of what your water table depth might be. So first of all, we're starting out with the fallow period. The idea behind drainage water management is when you're not growing crops and you don't need to get out there in the field, you can leave your water level high. You don't have to be draining. So you would put those stop logs in and keep the water level up to, say, 6 inches below the surface of the ground. And that's going to hold a lot of water back in the field. It's going to retain nutrients, and it's not going to allow those nutrients out and into surface water and ending up in the Gulf of Mexico. Come springtime, though, you're going to want to start planting. And with that water 6 inches below the surface, it's going to be really tough to get your equipment out there. So maybe 10 days or so before you need to get out and do some field operations, you're going to want to remove those flashboards. And you're going to want to do that, just allow the field to dry down, and then go ahead and do the field operations that you need to do. Now, to meet the standard, you could just go ahead and leave that draining all summer long. But here's a suggestion, this part in the purple here. What if we were to actually try and get some crop yield benefit off of this drainage water management infrastructure that we've put into place? To benefit water quality, we might actually be able to use it to benefit water quantity too, just a little bit. By holding that water back in the field, we might be able to get our crops to grow a little bit better. And so this is suggesting that with careful management and making sure to watch it and avoid prolonged root saturation, you might be able to get a pretty reasonable yield increase as well. Does mean paying attention though. Okay, then you're going to harvest your crops. Once you harvest your crops, then it's time to put your flashboards back in and bring that water level back up, that water table back up in the field. Another thing to remember is that if there's going to be manure applications on this field, the practice standard does require you to use the drainage water management infrastructure to make sure that you raise the flashboards before and during manure application. And that's going to help prevent loss of those nutrients through the system. So here's a picture for you. What does it look like? Here's a drain tile system. Kind of hard to know what's going on in this drain tile system. All of the action is underground. So I'm going to ask you to imagine what might be underground. Here I am standing at the outlet of the system. What's up there in the field? Obviously they had to do some drainage in order to make their crops grow, or for whatever reason they have some drainage out there. What might they have? Well, there are several types of subsurface drain systems that have been identified. One of them would be your pattern drainage system. Typically those things are out there on the landscape in a very symmetrical pattern, and they're designed to uniformly drain the land throughout. All of the land out there in the field is going to be affected by the tile drain. Then there are other systems that are pretty much random, and you just run a tile or two up in low spots of the field and drain out the worst of it, and that's about all you got. So it's important when doing drainage water management to understand the difference between the two. The drainage tile that's in the field affects only a portion of the field, just within a certain distance of the tile, and that depends on how deep the drain is placed, what kind of soil, those sorts of things. And since with drainage water management we're trying to affect as much of the field as possible, we're going to say that it really is only feasible to do drainage water management if we have a pattern drain system out there. So drainage water management is only recommended on fields with pattern drain systems. Here's some definitions for you. We're looking at a plan view of a hypothetical field here, and you can see the dotted lines represent a pattern drain system. You can see the main line running through, and then laterals coming off of those. And I want to talk to you about what zone of influence or impacted area must mean. Look at the little letters A and B. Those represent places where we might consider putting water level control devices. Take a look at A, for example, and note that I've also got on this schematic some contour lines. So we have not only a map of the tile here, but we also have a map of the elevations in the field. At A, the elevation of the field is 600, and then up at B, the elevation is 602, and so on. We have noticed that when putting these control structures in, a single structure will typically influence an area of the field that is obviously contained within the drainage system. It's not going to really affect anything if it doesn't have a drain system there, but also it needs to be within the 2-foot contour from the control elevation of the structure. And when I say control elevation of the structure, I mean what is the elevation of the soil surface at the lowest spot in the impacted area. The impacted area for structure A there would be that part colored in blue on the map. The impacted area or the zone of influence for B would be the green one. So, take-home message out of this picture is, for any given field or drainage system, it might take more than one structure to properly apply drainage water management to that field. Now let's go into a little more detail. In order to determine where to put those water control structures and what parts of the field are feasible for drainage water management, we need maps. We need lots of maps. We're going to need that topographic map. We're going to need that tile map. We're going to need information about soil. What I'm showing you here is a tile map and a topographic map overlaid. And this is a pretty simple example. These things can get complicated in a hurry. This particular one has just two main lines, two outlets, one here, and a bunch of laterals. So it is a pattern tile system, and it's all on one landowner. So that's real handy. Makes for a good example, wouldn't you agree? Here's how we work with that then. Here's the same one that I just showed you. Remember I talked about two main lines leaving the property. I'm going to talk about the one on the left first. Let's say we decide to put a water level control structure right there and try and do some drainage water management on this property. If we do so, recognizing that the tile drained area is that whole half of the field there, and recognizing that there's not more than 2 foot of elevation difference in the whole thing, then really we have the entire thing. The entire subunit is the impacted area. That's pretty handy. That's the ideal situation. Then you'd start to get into some more topography. Look at this example, the right side of the field. If we were to put a water level control structure on that main, there's a big hill over there. And the elevation of the field rises up above that 2 foot contour. So look what happens to the impacted area. First of all, you've got to chop it off because the tiles end. There's no tile drains over in the way right-hand side of that thing, you see. And then you also have to chop it off because the ground goes too high. And so there's only just a portion of the right-hand side of that field that is the impacted area for the proposed water level control structure. You need to be careful on recommending any sort of drainage water management for fields like this for several reasons. One is, if the impacted area is too small, you're going to be spending a lot of money for not a whole lot of benefit if you can't get a whole lot of acres in your impacted area. But the other thing is, if that hill rises up too high, think about what's happening. To do drainage water management on that, you'd either have to put a control structure on each one of those laterals, which would be way expensive and we'd never recommend it, or you'd have to just avoid doing it at all. If you have too much rise in the drain lines above that 2 foot mark, it could lead to ponding of water at the structure and potentially even blowing it out. So we just want to be careful. So we talked earlier about feasibility of drainage water management. And so I think this is a pretty important concept, and let's talk about it now again. The big one is economics. If you have to build a structure every few hundred feet, that's not going to be very financially feasible. And so we say flat topography is the important thing. If we can have 0.5% or even flatter average slope, that means that your single structure can impact more acres. We'd like to see at least 15 or 20 acres of impacted area per structure. We have an example in Illinois that has 140 acres. That's wonderful. That's what we want to see. It doesn't always happen that way. Well, before I go on though, it is possible to have drainage water management systems in steeper topography, up to 1%, maybe even steeper. But as I had explained, it does get more expensive, and at some point, it's cost prohibitive. We do need to know where the tile is, and it's important to have that patterned subsurface tile system, as I explained. Otherwise, we're not going to get a significant benefit. And so having a tile map and having a patterned system is important, and a limitation in some cases. Here's another thing. What about your neighbors? You need to know where your property lines are, and you need to make sure that if you're going to be managing the water table on your subsurface drain system, it's not going to have an impact on those neighbors. Goes back to having a tile map, doesn't it? We need to know. Does that tile go on to somebody else? Does it get too close to the property line? What do we need to know to make sure that we aren't going to be causing a problem on anybody else? The other thing to consider is, what about additional conservation practices? What if, tied into that subsurface tile system, we also have, say, the outlet to underground outlet for a terrace? Probably want to take a pretty good look at it and decide if doing drainage water management is going to make our terrace fail. So we're going to have to think about that too. It's going to affect the limitations on drainage water management in certain fields. All right. Now, drainage water management has been shown to reduce nutrient loads. That's great. Here's a theory. We talked about this before. The idea is we're going to try and hold nutrients in the field when drainage is not needed for production. So we're going to block that tile, or essentially render the drainage system inoperable, but just for a short period of time. It's a temporary thing. It puts the producer in control of when drainage happens and when it does not. It's been shown that if you have less flow coming from the drainage tile, then there's going to be less nitrates going to surface water. And as Hamid mentioned, hey, all that water's got to go somewhere, right? Why is it that we're getting less nitrates to surface water? Well, by the time that you remove that blockage in the tile or the elevated water table, that water has had enough time to sit around and allow the nitrate to then denitrify and is no longer existing in your surface water. So that's a benefit. Another thing to consider, though, is in order to do drainage water management, you do have to be able to raise the water table. If you have the sort of soil that is not appropriate for having a water table, you're not going to be able to get any benefit out of this type of system for reducing nutrients. It's been shown that if you have poorly or very poorly drained soils, that is good when you have sufficient organic carbon, that water moving through those layers and seeping down while you're holding back in the field, that moisture is going to pass through those reduced zones that are in the soil and reduce the nitrate load. It's not going to help so much if you have a type of soil that's not going to have one of those reduced zones. How are we going to measure the effects that we have out there on the field? I like to give an example when I talk about this of Russell 2. NRCS people are excellent at doing Russell 2. This is a model that we run all the time to take credit for sheet and rill erosion and the reduction that we do out there on the land. Are we out there with a beaker measuring how much less soil loss there is? No, of course we're not. We're doing it in the computer on a model. How are we going to do the same thing for drainage water management? How are we going to know how much less nitrate we're putting out there? Well, there is a model. It's called DrainMod. You may have heard of it. It takes into account all sorts of things, including the variability that might happen out there on a particular site, weather, soil type, what kind of management you're doing, lots of different things. The trouble with that is that it's very labor and time intensive. It takes some highly skilled specialists, usually months, to do an accurate DrainMod model for a site. I'm suggesting that NRCS doesn't have enough trained people to be able to do these models, to be able to measure our nutrient reduction, and so we're working with our university partners to come up with a way to streamline that sort of measurement activity. We do know one thing. A volume reduction in drainage is the same as a nutrient reduction from drainage water. And so we're hoping to cabbage onto that idea and come up with a way to estimate with reasonable accuracy how much nutrient reduction we can get by applying drainage water management. Jury's still out on that. Conservation Practice Standard 554 is our drainage water management standard. It is a management standard. You have to have some other things to support that management standard. First of all, you got to have a plan. It could be that Conservation Activity Plan 130. You also need to have some kind of infrastructure so that you can do your drainage water management, and typically that is done under 587, Structure for Water Control. And it is strongly recommended that you have nutrient management also. Conservation Practice Standard 590. So the plan, as I said, is kind of a big thing. You really need a plan. And in this plan, you're going to have information about your site. You're going to have some objectives. What are you trying to gain from having this plan? You're going to have a lot of maps. You're going to have a summary table of what happens with each of the proposed control structures that are going to go out there on the field. You're going to have some instructions to that producer, when and how high and all of that kind of stuff to operate your drainage water management system to get the objectives met. And you're going to have a signature page so everybody can show that they are in agreement with this plan. And I wanted to point out this website. The Illinois Extension has put together a pretty good drainage guide, and it's a template that can be used to do the drainage water management plan. Its contents match quite closely with the requirements for CAP 130. Here's just a little summary, kind of a highlight of the things that have to happen in 554 for purposes of reducing nutrient loading. Okay, you need to refer to the Conservation Practice Standard itself for all of the details, but here's some big ones. Raising the outlet must result in an elevated water table. Remember I said that before, that you got to have a water table in order to be able to raise a water table, and so you have to pick the right sort of site to be able to do drainage water management on it. The next thing, anything you do to put a structural measure in to accomplish drainage water management, you need to make sure that that doesn't restrict the free drainage. When you want to not do any kind of management of your drainage and just let it drain freely, any structure that you will have put on there must not restrict that free drainage. Releasing water. You need to make sure that you still meet the practice standard for Conservation Practice 606, subsurface drain. So there are provisions in that standard about velocity and tile, as you might recall. And if you can imagine, you've got a bunch of flashboards sitting there in your structure, and all of a sudden you decide, my fallow period is over, it's about time to plant, I'm going to take these stop logs out of here, and you all of a sudden yank them out of your structure. What's going to happen? Well, you're going to have a pretty fast velocity going to start with. That could be a problem. You might even blow out your structure. And so we need to make sure that when water is released, those flashboards are pulled gradually. Typical designs also include a solid pipe near the structure to make it so that the piping that is near the structure is more resistant to high velocity flow. Another requirement in the standard, remember I said about 10 days before planting, stuff like that? The standard allows up to 30-day window. So before you plant in the spring, you could come 30 days in advance and drain your field. And in the fall, you could wait 30 days after your final field operation. But that's a requirement of the standard. It's always okay to do it in a shorter amount of time. And the final thing, provision of the standard, as I mentioned before, is that you need to raise the drain outlet whenever you're going to be doing land application of liquid manure. I'm going to turn it over to Jerry Walker now.
Thank you, Ruth. And my topic is I'm going to discuss drainage water management with surface drainage systems. And during this presentation, I'm going to look at first a little discussion of surface drainage systems. I think we have quite a bit of confusion over what is a surface drainage system as it relates to drainage water management. And Ruth, everything that was presented in the subsurface drainage section on drainage water management the vast majority of it applies to what I'm going to talk about as well. Because a pure surface drainage system would generally be addressing surface runoff and not subsurface flow. And so most of the surface drainage systems you're going to run across are not going to be systems that you would be able to practice drainage water management. Drainage water management is only going to apply when you have a water table. So if you have a purely surface system, then you're not going to. That is just a surface system. You're not going to be looking at a water table. What you are going to see, though, is, and what we're going to talk about, is surface/subsurface drainage systems that do employ surface drain, field ditch, main and lateral, and sometimes subsurface drain. So it's these combination systems that would possibly be classified as a surface drainage system because they have surface drains in the way of field ditches, mains, and laterals, but actually that portion of the drainage system that you would be controlling would be the groundwater or the water table, and that's where you would get your drainage water management. I'm also going to briefly touch on other practices with the potential to have water quality impacts that would relate to surface drainage but would not be drainage water management. I'm going to run through just a few slides. I know we're a little behind, but basically when you have fields that you're going to need to do some type of drainage, a surface system, you're primarily worried about rainfall runoff. And so these can be anything from a terrace, basin terraces, waterways, diversions, things like this, that the surface drainage system is installed to gather and convey that surface runoff from rainfall to a safe outlet and get that water there in a way that's not going to cause an erosion problem or get on a neighbor. Now, in any type of surface drainage system that would also be a joint subsurface system where you would be making some effort to provide water table control, those systems must be capable of passing surface runoff from storm events. So any surface/subsurface drainage system that had the capability of controlling or being operated in a way that would control water table level would have to be able to bypass rainfall. I'm going to show you a few slides, and I will reference these later and give you information on where you can read more detail on both controlled drainage and just regular drainage. We have a number of good references that have a good bit of information on how to design, how to plan, and how to lay out and operate and maintain these systems. This is just an example of a parallel surface drain system that employs field ditches and outlet drain laterals. And this example, though, of a surface drain is not, these ditches are not terribly deep because they're designed to safely convey surface water, not drainage water. This system, on the other hand, well, it is actually in place to perform surface drainage. Something similar to that layout could be if this operation had a seasonal high water table or a confined water table, those ditches could be made deeper and then operated as a surface/subsurface drainage system. Now, it would generally be on flatter slopes than are shown in this example for a surface system. But the general layout and the orientation might be a little different, but those ditches could be deeper and could convey subsurface flow as well as surface flow. Our drainage water management standard at this time only applies if you are controlling a water table elevation. And that's done under criteria applicable to all purposes. Raising the outlet elevation of the flowing drain shall result in an elevated free water surface within the soil profile. So a purely surface drain system is not something that's going to apply for water table or for drainage water management. However, a combination surface and subsurface system could. What I'm showing right here would involve basically a combination system. You would have subsurface drainage pipe that are laid out across the field, then it's gathered up and conveyed to a surface ditch for disposal or for to take off the field. Now, the location that you would put your control structure with a combination surface-subsurface system would be in that surface ditch. You would have some type of water level control structure on the ditch, and you would maintain your water level, set your water level in the ditch, and then that water would then back up in the drainage pipe. And you'll note on this slide that the directions of the arrows are in two directions, and that sort of depends on what happens with your rain. And when you first raise the boards, then it starts backing up. The water goes out from the pipe. If you pull the drains back out, well, it'll go down and out. So that's kind of an example of a schematic of how this system would work. This is a field layout example of a water table management system. The dashed lines would be a subsurface drain pipe, and the black boxes would be water table control structures or water level control structures. You can see that you have them periodically, and so this would be the difference in this and what Ruth was showing would be, rather than this, the pipe drains emptying into a larger diameter pipe and conveyed down the slope with periodic water control structures along that main. But with this, we've got the individual pipes are dropping the water off into an outlet ditch, and then the water level control structures would be on those ditches, and as the water level, as you set your flashboards higher, it back water up into the drainage tubing and raise the water level similar to what was shown in the earlier presentation. Another possibility besides one that would use pipes would be a subsurface drainage system employing surface ditches that would have parallel field ditches in the field. And these ditches, I think Hamid showed some slides that would demonstrate this, that by placing the ditches deeper, then they would drain down the water table. With controlled drainage, in controlled drainage mode, if you had water level control structures on your field ditches and raised the water level, then early in the season or when the water table was high, then you could build the water table up to the elevation of the weir. Now, one thing that you have to remember with controlled drainage and then practicing drainage water management on these systems is that the water level that you'll achieve in the field is highly dependent on how much rain you get. So if you put your flashboards up high early in this, right after you've got everything planted, you get some good rain, you get your water level built up, and you reach this upper level. And then through the course of the season, the crop begins to get higher, but you go into a drought situation. Well, then your water level continues to drop, and without any replenishment, by the end of the season, you may have the control structure in place with the capability of controlling drainage, which controlling drainage would be actually controlling the discharge. And as long as you have a water table there to control, well, you're in good shape. But if you hit a dry period and you don't have any rainfall, then you don't have anything to manage, and that could be one reason that we've not seen the predicted yield improvements that had been anticipated in some of the studies. This is that same schematic earlier. I just took out the pipe and put in parallel field ditches so you could kind of see what it would look like. I left the contours in, but I didn't really check them to look at it to see how realistic that is. I would anticipate it would be fairly realistic, but you could put outlet ditches on the main. Again, when you raise the water level, it would back up into the field ditches, which then would increase the water level between the field ditches. And the distance up the field ditch that it would have impact would be completely dependent on the elevation set on the control structure and how far back it would go up. Also, in a surface drainage system, that the impact of the water level control structure as you raise it is somewhat dependent on the volume of storage that you have in that ditch as well. So there's a little more analysis to that, or impacts, I guess, that need to be looked at. Now, you'll note on this bottom ditch, as I looked at this schematic, we already had a water control structure here. This could be a situation where you really don't want to back the water up on this last ditch because maybe you've got a property line here that you don't want to raise that water level because maybe that water would move on to your neighbor. Now, I've got some slides here showing a typical, this would be a water control structure on a ditch with flashboards that you could raise the water level back in the ditch and then on field ditches. I've just got a few more slides here. Flashboard riser control structure. You'll note that in the upper left photograph, you have a split riser. This is on a bigger structure. This could be pretty wide for a single flashboard that would tend to warp if you've got too long a board in there, so they kind of split this. It also gives you the capability of maybe controlling your discharge when you did want to pull it down a bit. You wouldn't have to open both sides at the same time, so you could reduce your discharge a little bit. And these slides came from North Carolina State University, and we appreciate those. Mechanisms by which controlled drainage enhances water quality was discussed in our subsurface presentation. Yield increases can result if the conditions are right and we get some rainfall to help, and it happens to be at that point where that backed up water is available for crop response. Some numbers from North Carolina State would indicate that possibly a 5 bushel per acre corn yield increase, if you achieved one, would be equivalent to about 3.5 pounds of additional N uptake from the field. And then the primary benefit or reduction in N that you can really count on for certain would be a reduced outflow volume if you get enough rain that you're going to have a drainage system. Let me back up. Shouldn't do this. But I did want to make, this is a very, very, very important thing with a drainage system, especially as we get folks that are anxious to get out and put in and work with producers on drainage water management. We need to know that you've got some type of restrictive layer down that's holding the water up, and so that you have a manageable water table and something you can count on, and not just somewhere down below it's bound to be backing up or we wouldn't be seeing a water table. this goes with what I was telling you earlier about if you don't have rain, you don't have always a water table to control. You need rain to achieve our expected outcomes concerning crop yield anyway. Other conservation practices with potential water quality impacts might be constructed wetlands to treat surface runoff. Now this slide and the ones I'm going to discuss next are not tied to drainage water management, but to me they look like additional tools that might be of interest to the people that would be interested in drainage water management. If you've got surface runoff with water quality issues, then we do have other standards that could be used and could help. The National Engineering Handbook, Part 637, Chapter 3 on constructed wetlands has been recently revised. Also, Chapter 13 of the Engineering Field Handbook dealing with constructed wetland to make it clear that that practice is not only for animal waste treatment but also for improved water quality of surface water. Other structures, any of our surface structures, underground outlets, potential water and sediment control basins, anything that would store surface water runoff and provide an opportunity for treatment and or settling and or whatever, if the practice includes that as a purpose or where it applies, well, that's something that might be looked at. Natural wetlands provide water quality enhancement and nutrient removal, and constructed wetlands do as well. If a state hasn't looked at their constructed wetland standard in a while, they might want to take a look at the current national standard. It was updated fairly recently to clarify what you can do with that practice. And there is research ongoing in Iowa, Ohio, Illinois, and North Carolina, I believe, on that practice and its use for water quality enhancement relating to surface runoff. And I'm going to turn it over to Hamid, but I did want to clarify or make note that, oops, I guess I'm too late.
Yeah,
okay, I have references in the presentation that will be available for download that do reference those engineering handbooks and engineering field handbook chapters dealing with control drainage and sub-irrigation and those types of things that might be of interest to this group. Thank you.
Thank you, Jerry. I only have 4 more slides, so I'm going to move through this quickly. I will not be, it's kind of a wrap-up, but I think I'd just like to repeat a few of the take-home messages. Number one, we discussed earlier, this old, I like to emphasize the undesirable, unrestricted drainage situations. The thinking in conventional drainage systems disposal, and that is no longer sustainable, environmentally sustainable. It could be sustainable on my farm, but certainly not sustainable downstream on my farmers' farms. So my friends' farms. So we need to remember that. And I also like to mention what I have here says be aware and make aware. I think we need to. When we look at drainage water management, we didn't get a chance to talk about drainage coefficient, this desired capacity to drain in a 24-hour period, for example, which is a design criteria or design variable. We need to make aware that drainage water management could reduce drainage coefficient, thus enhance the potential for runoff. And I'd like to show you an example of how that's possible. On the left-hand side, I have the drawing of a drainage. This is a conventional drainage mode. Let's assume this was designed for a drainage coefficient of ½ inch per day, and No, we haven't raised the water table. The water table is at the drain pipe level. Now, on the right-hand side, I'm going to, let's say this is the winter conservation mode, and we have raised the water table by the flashboards. So when you look at these two, I'm going to put some points here, A and B. So I have point A, which is the original depth of the drain pipe. Now I have on the right-hand side point B. And now I went in and added a hypothetical, at point B, I added a hypothetical drain pipe. Basically what it says that during winter and during periods that could be any period that the water table has been raised, we practically have reduced our drainage coefficient. That means when water table raised to point B, the depth to drain pipe is equally raised to level B. That means you technically have less storage available, and that would increase the potential for greater potential for runoff. I'm going to complete here with 2 more slides. I think the challenge, Ruth talked about this, I think it's very important. We implement these practices, but how can we document effectiveness? How to measure or estimate the effectiveness of drainage water management on a given farm, and that would be reduction in water and nutrient losses. Ruth discussed modeling. I think modeling and experimentation obviously would be highly desirable, but that's demanding, needs data, would require time. At a minimum, we know that volume reduction is equal to nutrient reduction, and hopefully our NRCS specialists, ARS and university faculty can provide some guidelines or simple means of estimating the effectiveness of drainage water management. I have one announcement to make. Call it Drainage Summit. This is what is called Save the Date, Managing Water Harvesting Results. There'll be a meeting happening in I think it's in Bloomington, in the Minneapolis-St. Paul area, October 11th to 12th. And you can read this here. It says this meeting will explore the adoption of drainage water management techniques through discussions of incentives, past experiences, current situations, and future opportunities. So for all of you interested in this topic who will be tackling this would be a worthwhile summit to attend. Also, I'd like to give you the address. I know this is lengthy, but all these presentations would be available if you wish. But here's a reference to the Ag Water Management Team website, and I think that's all I have. We welcome all your questions, and I'd like to end at this time.
Thank you very much, Hamid. I'm displaying there where you can download a replay of this webinar, and we'll also have the handouts from this available. We'd like to open it up for questions now. If the operator could, if you would like to ask a question, you can press *1 and the operator will recognize you. While we are waiting for questions, we have 2 online questions already. And the first one says, some research has shown that nitrogen in streams may be the result of land application of quite some years in the past. Does anyone have any comment on that? And if there is actually a delay of 10 or 20 years in nitrogen moving from the land into the stream, does that present us a problem? Are any of our presenters aware of that particular issue and want to comment on it? Hamid, Ruth?
This is Hamid. No, I'm not quite sure if I understood the question, but for that length of period for nitrogen to be just sitting out there, I'm not quite sure what the situation might be.
Well, this listener says that that there's some tests have shown that N present in streams was land applied 20 plus years ago.
This is Pat.
Yeah, go ahead.
And the way that could happen, I believe, is if you had a long flow path back to the stream, and if your nitrates were down below the zone of any biological activity, you could possibly get those inert nitrates moving laterally, but you'd have to have a long flow path back to the stream. So it all depends on the soils and the proximity of the farm to the stream, quite a few different conditions. But I believe it could happen. I don't.
I think, though, one takeaway that we might refer to is the one of the slides I think that Pat, you showed about the proximity of streams to the Mississippi River and how and the flow out of those streams into the Mississippi River is having a very high potential for causing hypoxia. And I think there has been some research that shows that those areas that are very close to streams or have subsurface drainages that connect directly to the streams that get very quickly into the main tributaries of the Mississippi do have a very high potential for transferring nitrogen all the way down to the Mississippi, all the way down to the Gulf of Mexico.
That's right. I don't think that the studies would be pointing mostly at the Midwest, but rather there are streams in other locations with that long flow path.
Right. More of the peripheral areas.
Lateral flow. And,
okay. Our next question is, in Ruth's presentation, she had a slide about raising the or putting in the flashboards before the application of manure, and this listener asked the question, wouldn't raising the water level prior to the application of liquid manure increase the risk of soil compaction? Ruth, you want to comment on that? If you don't, I've got a comment on it.
Oh, I have one comment, and that is that the standard does require you to raise the water level. And when I say raise the water level, I mean raise the flashboards. I don't think you're going to have that quick of a response. Your drainage isn't happening like it's not going to be like the flow in a grassed waterway during a 10-year, 24-hour storm. So I think that if you raise these flashboards up and then immediately start land applying your manure, you're going to be okay. But I'd like to hear what you have to say, too.
Well, that's exactly what I was going to say, Ruth, is that, the response is not going to be immediate with the water table coming to the surface. So I think it's simply a safety factor that would allow us to reduce that potential for subsurface loss of manure. And as long as you don't raise the boards 1 week and then wait a week before you apply the manure, I don't think there'd be an issue.
The other thing I may not have said is that the provision is only for liquid manure applications?
Yes. Our next question is, a lot of farm folks have concerns with spring soil temperatures warming up, especially given cool, wet springs we've recently had. Water has high specific heat. What information do we have to respond to client concerns regarding soil temperature effects of water retention? It's a fairly complicated question. Any of you like to tackle that one?
This is Pat, and I think in those cases you would want to remove your boards the 30 days before rather than closer to the first field operation time. That would give you some time to warm up. And that should be adequate, but I don't have any scientific evidence on that.
And I think each one of these water management plans has to be an individual thing, and probably needs to be related closely to the soils and other hydrologic conditions that are that are specific to that site. And if you're in a soil that drains slowly, then certainly that time period, that lag period, needs to be allowed for in the springtime to allow the soil to warm up. That's all the questions we have online. Do we have any more verbal questions? Do we have any verbal questions that anyone would like to ask?
So far, there are none in queue.
Bill, this is Jerry. If there aren't any questions, could I make a comment?
We'd love to hear your comment, Jerry.
I neglected to make one statement in the surface water presentation, in that you'll note that subsurface irrigation wasn't discussed, though it is a form of water table control, but it requires, it's covered by a separate standard, that being surface irrigation and subsurface practice code 443. And if you were designing, planning, and installing a subsurface irrigation system, then you'd be looking at 443 plus the management practice that would go with that would be irrigation water management 449. And so that was the reason that subsurface irrigation wasn't discussed in this presentation. I intended to say that and I forgot to. Thank you.
One more chance for verbal questions or online questions. Any burning questions that anyone needs to ask?
And so far, there are still no questions on the phone.
Thank you, ma'am. With that, I think we're going to call it a day. I really appreciate everyone's participation. And again, you can refer to this website that's on the screen right now within a few days and be able to get a replay of this webinar, as well as remember, if you want CCA credits, to send your sign-in sheets to Holly Clickendall here at the East NTSC. Thank you very much. We'll sign off for today.
Thank you for participating in today's conference. You may disconnect at this time.